destroying foreign bacteria and viruses, even if there's single mutations that make the flu this year different from the flu last year. It makes one cold virus different than another cold virus. It's this incredible specificity and memory, so that once you get rid of the virus or the bacteria, you'll never get it again, which is why we get vaccination only a few times in our lives. So once the immune system recognizes, it eliminates all of these bacteria and viruses. And now for the first time, the research that's been done by our community using the immune system is now equipped to take on this deadly enemy of cancer. And what I want to tell you about is a story about how this occurred. So everybody knows someone who has cancer. 1 in every 3 women will get cancer in their lives. 1 of every 2 men will get cancer in their lives. 8 million people will die this year from cancer and every year following. That's how deadly this disease is. So about 150 years ago, people started trying to deal with this disease. At the beginning, we started cutting it out with surgery, and we started poisoning it with chemotherapy. We bombarded it with subatomic particles through radiation, and we've hit it hard with targeted drugs to try to impede on their survival. People are living longer. Certainly in some cases, people are being cured of the cancer. But these therapies ravage the body. They cause terrible side effects and horrible disease in and of themselves. And in fact, in most people, the cancers eventually come back and kill you. So why is cancer so tough to beat? In some ways, cancers look just like any other cell in the body. They start out just like a normal lung cell, or a normal kidney cell, or a normal skin cell. But then it starts mutating. In fact, cancer cells are a mutation machine. They start changing, they grow, they change shapes. They start migrating to different parts of the body. So a cancer cell in the skin can go to the heart, can go to the brain, can go to the liver, can go to the lung. And as they mutate, they escape all of these drugs that we try to give to destroy them. And just keeping up with it is impossible. And so cancer really turns out to be not just one disease, but many, many, if not millions of diseases, where each cell is its own cancer factory. And the difference between one patient and another is clear, but even within one patient, the cells are different from one another. So does this sound familiar? Doesn't it sound like the immune system's ability to detect and destroy viruses and bacteria and parasites? In some ways, cancers are just like that. So could we take the immune system and use it for good? So the first indication that the immune system could defend the body was some work done over 150 years ago by William Coley. He was a surgeon. He may not have been a great surgeon, or at least surgery wasn't great at that time because some of his patients got infections after the surgery. But what he found was that those patients that got infections often did much better than the ones that didn't get infections. And he hypothesized that maybe the excitement of the immune system in trying to eliminate the infections was involved. So he started infecting people on purpose. He started taking his patients and giving them bacteria after the surgery and looking to see what happened. And fully 10% of his patients, the cancers never came back, suggesting that maybe actually inciting the immune system was going to be a positive outcome. Unfortunately, most of Coley's peers at the time didn't believe it. They thought there weren't enough patients having an effect, and they really didn't think the immune system was doing much. But since the 1800s, we've learned a lot more. First of all, we've learned that the immune system is a highly regulated and balanced system. It's a system that has to deal with viruses and bacteria, and so we constantly are trying to do that, so we can't have too weak an immune system. If we do, then the viruses and bacteria will take over. But it's also a system that has to deal with its self-tissue, so that we don't recognize and destroy our self-tissue and get autoimmune diseases like multiple sclerosis and arthritis and type 1 diabetes and 80 other diseases. And if we have too much of an immune response, then we start getting those diseases. So at the end of the day, we don't want glitches in the immune system. We want to keep it highly regulated, highly balanced. We want to keep it in check through on and off switches. And in fact, the goal of the immune system is to keep this balance and to keep it functioning in a homeostatic way. So where do my lab and our work come into this? Well, about 2 decades ago, we started looking for some of these switches. We wanted to ask, what were the things that turn on the immune system when you want to, and potentially turn it off when you don't want it to? So we started out with turning on the immune system. And it turned out that each cell in the body, each T cell, which is the cell that's really important in recognizing viruses and bacteria, have a complicated set of on switches. They're like an ignition key followed by a gas pedal, where you press down on it and the immune system starts getting activated and starts going out, recognizing and destroying it. It's a very potent response, this on system for the immune system. In fact, one of the reasons that we reject organ transplants is because that system is so strong when you put in a foreign kidney or liver into somebody. So the first thing we did, and others, was to develop drugs that could block that on signal, that could prevent the immune system from going too strongly against in this case, organ transplant or autoimmune diseases like rheumatoid arthritis as an example. And that was very successful. But of course, the problem with that was it didn't deal with the other side of the equation. And the other side of the equation are the brakes. And trying to figure out what are the brakes that actually control the immune system as well. Because if we could understand the brakes, we could also unleash the immune system when we wanted it to. So I'll never forget the day the graduate student of mine, Teresa Lunis, walked into my office to show me some data from an experiment. I think she had done it 4 or 5 times because she was afraid to come in because the results were opposite what we had expected. We thought we were looking at another on signal for the immune system, a molecule called CTLA-4. It's present on activated T cells and it looks a lot like one of the other gas pedals. So we thought for sure that this on signal this molecule was going to be another on signal. But when she came in with data showing that if she blocked this on signal, putative on signal, it didn't shut down the immune response, it actually made it better. And it was really the first demonstration that these cells actually had brakes that could be engaged and shut down the response. That single result, that single day, changed my career for the rest of the time since 1994 when we made that discovery. And it led us to believe for the first time that maybe we could control the immune response in both directions, both the on switches and the off switches. It seemed logical that the off switches were important. Let's face it, I already told you that cancers look a lot like normal cells. So the immune system is designed not to see self as foreign. So these off switches made sense to be exploited by cancer. And in fact, it turns out that cancer does exploit these things by cloaking themselves with molecules that turn on those brakes and shut down the immune system. Well, less than 2 years after our discovery of CTLA-4 as the first inhibitor of immune responses, Jim Allison, working at the time at Berkeley, demonstrated that if you took a molecule, an antibody in this case, and blocked that brake, prevented the brake from getting turned on, not only did it goose up the immune systems, but it allowed the immune system to destroy cancers. And it changed the whole field because for the first time, CTLA-4 blockade, as well as a cousin molecule, PD-1, which had a similar effect, could be used as what we call checkpoint inhibitors, molecules that could turn off the brakes and allow the immune system to go when it otherwise wouldn't be going. There are now 4 approved drugs. The first approved drug was against CTLA-4 itself. It's a drug called ipilimumab. I know it sounds like a Dr. Seuss title, but all these things have weird names. Since then, there's 3 additional drugs that have been developed against the PD-1 pathway, and together these drugs have revolutionized cancer treatment, and now, for the first time, really show that the immune system could be employed to get rid of cancer. And this is what it's done. This is what a graft used to look like for cancers, where we would develop new drugs, give them to patients, and they might live 6 months longer or a year longer. But inevitably, the cancer was going to take over, and it would mutate and change and go away. What these checkpoint inhibitors have done has really changed the outcome in many people. People who have melanoma, people who have non-small cell lung cancer, certain bladder cancers. We've gone to a situation now when either used alone or in combination, we can see significant percentages of patients that have long-term, durable cures from these cancers, many out over 10 years now. If you take the example of metastatic melanoma, those people who had this disease had less than a 5% chance of living past 10 years. Now it looks like we're going to be in the range of 40% of those patients alive at 10 years. So this is a change. It's not just a change in the type of drug, but it's a change in the outcome of these kinds of drugs. One example is former President Jimmy Carter. who suffers from metastatic melanoma, which went to his brain. And he was treated with one of these checkpoint inhibitors. He recently said, "I had 2 weeks to live, and here I am building houses for Habitat for Humanity." This is a revolutionary treatment for those patients that respond. So it's very exciting. We now have a new set of armament in our toolbox to be able to go after and start to recognize, attack, and destroy cancers. And that would be great if that's where the story stops, but it doesn't. There's more. I want to tell you a story about a little girl named Emily. So in 2010, Emily was diagnosed with a cancer called acute lymphoblastic leukemia, ALL. It's a devastating cancer of the blood. In fact, after 2 rounds of chemotherapy and 16 months of treatment, one day her mom and dad, Carrie and Tom, came into the doctor's office, and the doctor told them that there was nothing more they could do, that there were cancers riddled throughout her body, pounds of tumor that could be identified in her blood. And they sent her home with not much left to do. But she was lucky. She got involved in a clinical trial at the University of Pennsylvania. It turns out that ALL, unlike the other cancers I've been telling you about, don't have as many mutations. So you can't use the checkpoint inhibitors to excite the immune system to go and attack them. So a colleague, Carl June, at the University of Pennsylvania at the Children's Hospital there, had an idea he'd been working on for 25 years. What if you could take the T cells out of Emily's body and use them to destroy her own cancer? I know it sounds like it's something out of a science fiction novel, but what if we took her cells and engineered a receptor in them that could recognize the ALL cancer cells? What if we could then take those cells that have been engineered and grow them up 1,000-fold and then inject them back in? What might happen? Well, Carl did that with Emily. They took her blood, they took her cells out, they put in this receptor that saw a protein on the cancer cell. They grew up those cells into large numbers, and they injected them back in. Now, I should tell you, Emily got incredibly sick. I mean, imagine what would happen if you put in all of these killer T cells into a patient that's got pounds of tumor. There was an immediate attack and response, and there was just toxic material spewed out of the cancer cells, spewed out of the T cells, trying to kill the cancer cells, and Emily actually went into a coma, and they were worried that she was going to die. But a little while later, she came out of the coma, and the tumors were gone. And these so-called CAR T cells have now become an incredibly exciting area for research, where now patients are routinely with the ALL cancer and now other blood cancers are being enrolled in clinical trials that are designed to engineer their cells, put in a receptor, put them back in, attack and destroy those cancers. And in fact, something close to 70% of patients who are treated with this now are having their cancers go into remission, and we hope it'll last for a long time. And one of the reasons we think it might last for a long time is because these cells are like a living drug. They get into the patient, they do their thing, but they don't die and disappear. They just hang out. And if a cancer cell comes back, and if a cancer cell starts to grow, then those cells will be reborn, and they'll grow and they'll start attacking the cancer. So like in a vaccination, right? Like when you get poliovirus vaccine, if that poliovirus comes back, there are still T cells in your body ready to recognize that poliovirus and eliminate it. And that's what these cells do. So Emily's story is now in all the medical books. Here you have something that 6 years ago didn't even exist as a therapy, and now it's becoming a fundamental aspect of how we can think about treating cancers in the future. But as I've said already, and I want to say again, this is just the beginning. The new things that we're trying to do now are going to make this early stage of cancer immunotherapy seem primitive. For instance, one of the trials that's being done by the Parker Institute, which I'll tell you about in a second, is one where we try to combine the checkpoint inhibitors with these CAR T cells. But not to do it randomly, but to do it quite surgically and specifically. In fact, we're using this new exciting technology called CRISPR to go into the DNA of those cells that we've taken out of the body and selectively just eliminate the checkpoint inhibitor. So that the cells we put back into the patient have that chimeric receptor that'll see the tumor and destroy it. But it won't have the brakes anymore. So we won't have the ability to have the immune the tumor cells shut down the immune system. So it's exciting. It's an area that I think will explode, and it's an area that's going to allow us to start treating multiple different cancers that right now can't get treated because these T cells won't make it into the site or get activated enough to destroy the cancer. So I want to end by telling you about how can we accelerate this? How can we actually make cancer immunotherapy a routine and reliable treatment for most cancers that we now get today? And this is where Sean Parker comes in. I know everybody knows Sean Parker, a very successful tech entrepreneur. But what people don't know is that Sean, at a very early age in his teenage years, suffering from asthma and other immunological related diseases, actually started getting interested in the immune system, not just to understand his own disease, but when realized the power of the immune system, and when you get sick, you can tell how powerful the immune system is if you have asthma. How could you actually now tap into that to treat other diseases? And he landed on cancer. He decided right then that maybe we could use the immune system to cure cancer. When I first met him in 2010, he was already convinced that this was the way to go and that there would be ways to build an institute that would allow us to exploit all of the discoveries that were being made. Remember, in 2010, ipilimumab wasn't yet approved. We didn't have the PD-1 molecules out there yet. CAR T cells were just a thought in college and other people's minds. So this was early days. Okay? It seems like we've been doing it for a while, but it hasn't been that long. So in 2013, he began to work on the institute itself. And how would he form it? How would he develop a place where the best scientists could come, work together, and hopefully create new discoveries that could change the path of a patient's lives? That ends up now being the Parker Institute for Cancer Immunotherapy. Sean has challenged us to take chances, to make big bets, to take big risks. He's given us enough resources to try things differently than we've been doing before. We don't want to be constrained by the typical constraints that certain funding agencies like the NIH or industry might put, but be able to try things differently, to take people's wildest ideas and give a shot. Because it's when you do something you didn't expect, when you have a break when you thought you had a gas pedal, that's when big changes happen in science. We've done this by trying to create a sandbox, a place where the people in it can share, trust each other, be confident that their work is going to make a difference. We've tried to create a sense of family, a core group of people that are comfortable working with each other, that are smart, that are committed and dedicated to advancing the cures for cancer. This is in the nonprofit space, so we're really focused on trying to move things as quickly as possibly into the clinic. You know, what stays in Pisces, what happens in Pisces stays in Pisces. We want to make sure that the people around the table are really focused on the problem at hand. And what Sean says is he wants to hack cancer, just like he's hacked music and he's hacked other things in his life, and really come up with a better process to do this. So it starts out by having great institutions, and we have 6 of the greatest institutions in the country participating in this, from MD Anderson and Sloan Kettering to, of course, UCSF, Stanford, UCLA here on the West Coast, and University of Pennsylvania. These institutions combine incredible research and clinical assets and a history of translating discoveries into patient care. Each center has a director. Again, you'll see up here Carl June and Jim Allison, 2 of the people that I've talked about earlier. But each director at each of these centers is at the top of their field, and they bring with them young people and innovative projects that otherwise might not be done. What we're trying to do is to facilitate bottom-up, bubbling up of new projects and new ideas, but yet do it in a team science roadmap that we've all created together to work on together. We encourage everybody to share ideas and papers and inventions and data as early as possible, well before they're published, so we can get a head start on what the next discovery might be. And of course, you can't do this in isolation. We need to partner with others. So we're partnering with different industries for new technologies and new innovative research that comes out of those industries. We're partnering with companies that have access to tools for computer and intelligent data analysis. We're partnering with other institutions that might have a unique perspective on how to identify and treat cancers using the immune system. And mostly, we're trying to make the Institute interdisciplinary. I already mentioned how we learned so much from autoimmunity infection that led us to think about new ways to treat cancer. Well, there are a lot of other scientific fields that matter. Nanoscience, metabolism, radiation biology, all of which impact on the ability of the immune system to recognize and destroy cancers. We want people who are involved in all of these fields. We want people that are involved in the microbiome. These are the bacteria that live in your blood and your gut and your skin, which we now know are essential to making these immunotherapies work. If you don't have the right microbiome, the checkpoint inhibitors don't work. What's the connection there? So we need microbiologists involved. We need geneticists involved. We need computer scientists involved. And the Institute is set up in a way that we can bring all of these people together to partner with us. And most importantly, we need the patients to be a partner as well. We need the patients to be involved in our science. We need them to be involved in our clinical trials. So why now? Why is this the right time for the Parker Institute? Why is this the right time to invest in cancer immunotherapy? Well, the science is there. I've tried to convince you we've made extraordinary advances there. But frankly, we're in an amazing revolution, biomedical revolution. It's not unlike the revolution of the late 1800s and early 1900s in the Industrial Revolution. We have more access to knowledge. We have more access to tools. We have more access to great ideas than ever before in biomedical science. The genomic revolution itself, the sequencing of the genome, so that every cancer cell can be sequenced and every normal cell can be sequenced, so we can see where the mutations are and what's different between the cancer cell, so we can attack it with the immune system. We have computational technologies that are out there, created in fields quite far from medicine, which are technologies that can really be used to interrogate and change data into knowledge in our understanding of the immune system. And then we have leadership. We have people like Vice President Biden and his cancer immune shot, the National Cancer Institute, the FDA, who are all committed to new investments, and they're all committed to making new programs that can take the discoveries that are made in the laboratory and move them into patients. And finally, we have extraordinary commitments from the philanthropic community to support and accelerate the research. I've mentioned Sean Parker, of course, and the Parker Foundation, but people like Priscilla Chen and Mark Zuckerberg, and people like Mark Benioff and Lynn Benioff, who have spent so much of their time and energy trying to make science better, to make medical care better, to change the course of disease, that it's with the input of these people that I think we have a great chance of making a difference. So in the end, the immune system is truly an intelligent and very technology-based platform. The technology of the immune cell is enormously complex. But now we're starting to be able to decode that, and we're starting to be able to utilize it to attack cancer. Unlike the static brute force approaches we've used in the past of these therapeutic chemotherapies and radiation therapies and the like, now we can start letting the body itself start dealing with the cancer cells. We're fighting fire with fire. We're trying to achieve durable remissions. And this is why I think we can succeed where others have failed. And this is what cures will look like. Thank you.